Alright guys, you're welcome back, and the last time we talked about the Boolean retrieval model, and one major drawback that we identified is that it's not possible to rank the document. But now we'll move on to a better model, which is the best match, and this is commonly used, and the advantage is that it is more effective than the exact match, and it's easier to use. They support full query text like text. The disadvantage is the efficiency is always less than the exact match. They cannot reject a document early. It still has to rate the document on a scale. So the Boolean structure query can be part of a best match. You can implement that in the backend. So let's see the vector space model, which is an example of the best match retrieval model. What this is saying is everything is a vector. You understand what a vector is? A vector is in Python is a tuple. It's just you have you can if you have the simplest vector that you can have is a two-dimensional vector where you have the coordinate of x and y. So but when you have more than two-dimensional, when you have z, you have x, y, z, that is a three-dimensional vector. And when you have more than that, you can have an n-dimensional vector. So in vector space model, everything, your query, your document, your terms, they are all vectors in high-dimensional space. And how do you do that? So you pick every term and you draw them on a high-dimensional space. The document too, you draw them on a high-dimensional space, as well as the user query. So as you can see, by drawing everything on a vector space and a high-dimensional space, you can measure how close some terms are and how close the query is to some document. So the geometry of the space in this is a similarity measure between documents. You can see which documents are closer to each other, and the documents are ranked based on their similarity with the query. This was invented by Gareth Southon in the 1960s. So what are the issues for vector space model? Well, how to determine important words in a document. How do you know which word is important? How to select the basis vectors, the number of dimensions. How to convert the object into vectors. That's a very important problem. Not all terms are equally useful for representing the document, so less frequent terms allow identifying a narrower set of documents. So this talk about whether we should remove stop words or not. The importance of the index terms is represented by the weight associated to them. So the weight tells us is a measure of how important the terms are. How to determine the degree of importance of a term within a document and within the collection. How to compare objects in the vector space. The degree of similarity between a document and query, which is very essential to know the order of ranking of returning document. And in the case of a web, what actually represents a collection. So let's see an example here. Here we are considering essentially three terms. We have three terms in our collections. And we have two documents. As you can see, this is document 1 and document 2. And we have one user query. So our work is we're going to plot this into the vector space model and measure which of the document is closer to the query. Which of these documents D1 and D2 has a closer match with the query, and do a ranking of their match. So first, what you do is that we take document 1 and we get all the uh, terms in it. We can split them into tokens. So let's say, for instance, in document 1 we have T1, T2, and T3. So we list out all the terms in the collections in the corpus. So T1, T2, T3, we're just limiting them to this T1, T2, T3. So we're saying that in document 1, the weight associated with term T1 is 2, so 2 times T1. That weight could be determined by something else, which we'll see. Maybe the frequency, maybe the TF-IDF, time frequency, inverse document frequency. But there's a weight attached to term 1. You see here, T2, 3 is attached to it, and 5 is attached to term 3, which means that T3 has more weight in this document 1, in classifying document 1. In document 2, definitely T2 has more weight in classifying, in dictating document 2. So now, we now check here the query. Now the user supplies queries, it only supplies term 3, maybe the frequency of what the user supplies is 2 times of term 3, and the user never supplied this. Okay, so maybe all these weights, we can just simply take it for now, just the term frequency, that how many times the term occurs in the document. So what we now do to create a vector space model is we take document 1 and we plot it here on our high dimensional space. So you can see by the time we plot in T1, so we have, this is T1, this is T2, and this is T3. So if T1 is 2, plotted on 2, T1 has 2, T2 has 3, and T3 has 5. You get this for document 1. This is the vector for document 1. Similarly, for document 2, we get this vector. This arrow shows the vector for document 2. And once you plot the query, this arrow shows the vector for the query, which is just 2. All others is 0. So, which is what for T3. Now, so we now ask a question: is document 1 or document 2 more similar to the query? How do you measure the similarity? Just measure the degree of the size of the angle between the query and each of the document, and definitely you can see that the angle between the query and document 1 is smaller compared to that of document 2. So how to measure the degree of similarity, whether the distance or the angle. So that's essentially what the vector space model is all about. So first, you assume T distinct terms remain after preprocessing, and we call them index terms or the vocabulary. So you want to be sure that you have T distinct terms in your corpus. And these orthogonal terms form a basis of our vector space. That is, the dimension of our vector space is going to be the number of terms, unique terms, since we already removed duplicate. That will be the size of our vocabulary. As you can see here, the size of our dimension here is 3, T1, T2, T3, because we have 3 unique terms. That will be the dimension. So each term I in a document or query J is given a real valued weight. So that is Wij means the weight of term I in document J, or the weight of term I in query J, either of the two. Because as you can see in this space, we represented the weight here as maybe the term frequency, the number of times it occurs. the term occurs in the document or in the query. And we multiply that by that term. So each document and query are expressed as t-dimensional vectors. Said that before, and you can see here for document J, you are going to have weight for each of the terms, for each from each of the term up to the last term, from term 1 to T. So this one means a weight of term 1 in document J, weight of term 2 in document J, until weight of the last term in document J. So the document collection. So the collection of n document can be represented in the vector space model by the term document frequency, and this is the term document frequency. So we have all the documents in our corpus on this column, and we have all the terms in our corpus as a row. Then we now have the associated weight of the term with the document. So an entry in the matrix corresponds to the weight of a term in a document. So for instance, this is the weight of term 1 in document 1, and this is the weight of term 1 in document 2, this is the weight of term 1 in document N, and so on and so forth. So this is the weight of term T in document N. So when you have a 0 entry, it means that that particular term has no weight, no significance in the document. That is, maybe it does not exist, so it won't count. It won't influence the similarity measure. So how do we now measure the term weight? There are different ways that we can measure, we can decide these weights. So this entry W1, W21, WT1 up to WTN. There are different ways by which you can determine them. One common way is to use the term weight, which is called the term frequency. Essentially what this does is that it says that more frequent terms in a document are important. That's the assumption. That is, when a term continuously reoccur in a document, it means that those terms are indicative of what that document is about. For instance, if you keep having more terms like baseball, like field, like coach, like all the spectators, like players, that should tell you that those terms are indicative that the document is about a game, about a sport, and not about food. But if you have a document that is talking about knife, fork, talking about plate, kitchen, talking about cooking, you know that that document is more about food than compared to like wrestling. So definitely. So the frequent terms in a document can be a very important indicative of what the topic of that document is. So what Fij is, that is the frequency of term I in document J. Now we use the term weight at the back end when preparing our vector space model, our information retrieval system based on vector space model, because now when we're preparing our model, we have all the documents available, so we can actually index all the terms and check the frequency of the term in each of the documents. You may want to normalize the term frequency by dividing the frequency of the most common terms in the document. This is just a common mathematical stuff that you do when you need, whenever you have to take frequency. You always try to either normalize by the total number of terms, or you normalize by the maximum frequency, by the maximum frequency of the most common term, so that there won't be any kind of bias towards the most common one. So you want to normalize it. So F is the frequency of term I in document J, and you normalize that by the maximum maximum term in the set of frequency of terms. So, and this gives us the term frequency of term I in document J. Another way by which you can decide the term weight is to use the inverse document frequency. We'll talk about the term frequency. Now we want to, another way is to use the inverse document frequency. And what the notion for the inverse document frequency says is that terms that appear in many different documents are less indicative of the overall topic. So that's what this inverse document frequency actually captures. That if a term appears in many different documents, then it may not be indicative of the overall topic. So, and how is this calculated? So the DFI is the document frequency of term I, that is equal to the number of documents containing term I. So, and you now calculate the inverse. So the inverse document frequency of term I will be log of the total number of documents divided by the number of documents containing the term I. So that is how you decide, you calculate the inverse document frequency of term I. So in an indication of term discriminative power, log used to dampen the effects relative to tail. So it essentially is n divided by the document frequency of term I. That's how you, if you are using the inverse document frequency to determine the weight. Then the last way you can decide the weight, don't forget that what we're trying to do is to find different ways by which we can measure and calculate this W11 up to W2N. And the last way we can do that is what we call the TF-IDF weighting, which is a combination of the combined the term importance. A typical combined term importance indicator is TF-IDF. So what it does is take the term frequency and the inverse document frequency and multiply the two to determine the weight. So the TF-IDF is the term frequency of term I in document J multiplied by the inverse document frequency of term I. Remember that the inverse document frequency does not have to do with a particular document. It deals with the entire corpus. Since you have the document frequency of term I is the number of times the term occurs in all the documents. So a term occurring frequently in the document but rarely in the rest of the collection is given high weight, and that's the implication of the TF-IDF. So what do we mean by a term occurring frequently in the document but rarely in the rest of the collection? So you know, if a particular document is containing a frequently certain term, then it means that that document is about what that term actually depicts. So, and if the term is not occurring in other collection, then that document is like representative of that term. So that's why we say that a term occurring frequently in a particular document but rarely in the rest of the collection is given a high weight. So this will help dampen the effect of the stop words, because the stop words like to, be, d, they will occur equal amount in other documents, so they will be given less weight. Alright. So by experiment, TF-IDF has been found to work so well, and this has been the state of the art that has been used in many work to implement a vector space model, that is to be able to decide the weight of the document, the weight of the terms in the document. So let's see an example now. So let's see how we can compute a TF-IDF, and we'll continue from there the next time. So let's quickly see how we can compute this. So given a document containing terms with these given frequencies, so that means in our document, we have term A that occurs 3 times, terms B occurs twice, and term C occurs 1. So now let's assume that in the collection, that is in our corpus, we have about 10,000 documents. Okay, and document frequency of these terms are So what it means is that in all the collections in all the 10,000 documents, term A occurs 50 times, term B occurs 1300, term C occurs 250. So now we need to compute the TF-IDF, and before we do that, we first of all compute the term frequency and the inverse document frequency. So how do we go about this? Okay, so here we are actually looking at a particular document. So this is our document J, in which you have the term frequency. Here we're looking at the entire corpus and giving us information about how the different terms are appearing in the entire corpus. So how do we do that? We just follow the formula. For our TF, term frequency of I in J, that one is known, that one is very easy. So the term frequency of term I of term A in document J is 3. The term frequency of term B in document J is 2. Term frequency of term C in document J is 1. So we know that one for sure. So we can easily just get our A. So we have our term frequency is 3. Okay, we can see it here. For our B, the term frequency is 2. For our C, the term frequency is 1. And just like we said, we normalize by the max. So the one that has the max is what? Is A, which is 3. So we just normalize this term frequency by 3. Divide by 3, which is the max. So this gives us the term frequency of each of the terms. Then the inverse document frequency, we just key in the formula, which is the total number divided by the document frequency. So the total number is 10,000. It's 10,000. 10,000. That is our N. So the document frequency is how many times does A occur in all the document? 50. B 1300. C 250. So by the time we do this, we get all these values, and we just multiply these values with this to get our TF-IDF. So this represents the weight. So the weight of term A is 7.6. Weight of term B 2.0. Weight of term C is 1.8. Okay, so as you can clearly see, you will see that term A, which occurs less in other documents but more in document J, has the highest weight. Let me say that again. Term A, which occurs least in all the document but more in document A, has the highest weight. And on the other hand, document B, which occurs more in all the document but less in document J, is given the least weight, the least power rate. So we're going to stop here for now. Thank you for listening, and see you in the next one. Thank you.